Well, good morning, or good afternoon, good evening, wherever you happen to be in the world. I am delighted to welcome you to this technical briefing. My name is Dame Judith Hackitt. I'm sure, and I know from having looked at the participant list, that there are many on this call who I know already. Among the 275 people who have registered to join us today, which is absolutely great. But for those who don't know me, I've had many roles in the past and continue to have roles in my current working portfolio. But for the purposes of today, I am a fellow and trustee of the Royal Academy of Engineering, and I chair the Engineering X Safer Complex Systems mission, which we're really excited to be telling you more about today. Before I do that, though, I want to go through one or two housekeeping points and move on to the next slide. So I am sure that you are all experts in the use of Zoom and Teams by now, but please note that for the purpose of this session, your video will be off and your microphone will be muted throughout. So if you want to pose questions to our speakers, and we hope you will, then click on the Q&A bar in the toolbar at the bottom of the screen and type your question in the open field. Even if you don't have questions yourself, but you are thinking of raising questions, please do keep your eye on that toolbar and look at those questions, because if you vote for questions that are already there, they will rise up the priority list and are more likely to get answered during the session. I'd also ask you to note that we're going to be recording this session and it will be uploaded onto the website if you've enjoyed it so much that you want to view it again or even tell your friends about it. So now on to complex systems. And on the next slide, as you well know, the rapidly changing and increasingly complex nature of the world we live in means that complex systems operate at ever greater levels of uncertainty and unpredictability all around us. In early 2020, the COVID-19 pandemic has shifted the frame of reference for us all and has demonstrated how that increasing complexity and interconnectedness of the world we live in has made us all more vulnerable to systemic shocks of natures that we thought about before, but now we know it for real. So this is a major global safety challenge. Our mission is to develop an understanding of the root causes of systemic failure and to take collective action to prevent and mitigate against future events with similar potential to harm, and also to look at complex systems on all scales. Our work is to enhance safety in complex infrastructure systems, and this becomes more important and more urgent than ever, we believe. So on the next slide, faced with this context and faced with this challenge, which I have to say that we started on even before COVID, and with many independent sources already pointing as complex systems as a risk to safety, in spring 2009, Lloyd's Register Foundation and the Academy partnered to explore the topic further and founded the Engineering X Safer Complex Systems mission. I want to be clear at this point that this program of work is not about systems engineering, and I'm sure there are some systems engineers with us, but this is about complex systems that involve many different disciplines. Not all of those disciplines are technical. Some of them are human systems, they are social systems, they can be regulatory systems, and many more. It is also about all of those different systems and how they interact, regulatory with human, regulatory with social, and so on, and the consequences of that. So this is a very big and a very broad topic. After 2 years of gathering evidence through 3 workshops and 1 commissioned piece of research, we're now moving from the learn phase of our work into the build phase of the program. So far, it's been a fairly slow burn, as we've had to work out exactly what it is we're trying to do and work out where and how we can make the most impact. But we're really delighted to be in the position to launch our new strategy today as part of this technical briefing, and also that all of the other work that has supported Engineering X has brought us to the point of this milestone. So let me now say something about those pieces of work that have informed our new strategy and brought us to this point. On the next slide, you will see that there are 3 pieces of work which have informed our new strategy. All of them are being made available today and are on the web page shown at the bottom of this slide. On the left, you'll see Safer Complex Systems, an initial framework. This is a report that was produced by the University of York for us, and it's an important first step on our journey of supporting society to better manage complexity. The report generated 6 recommendations for the Safer Complex Systems mission, which we've now factored into our ongoing work. It also made a start on creating a framework to enable people in different sectors and from different disciplines to analyse systemic failure and to discuss how to manage safety in their different contexts. And Roger will speak a little bit more about this framework later on. The report in the middle of this slide is a summary of a workshop on exploring the safety of supersized structures, which the Engineering X programme delivered in partnership with BRE and UCL. This workshop focused on the fact that few large structures exist simply as engineered structures. Most of them form part of a complex socio-technical system, and the consequences of failure extend far beyond the mechanical failure of the structure itself. Finally, on the right is the summary of the workshop we held back in September 2020, where we had 140 participants from around the world who helped us to gather feedback on the other 2 reports that I mentioned earlier, and to help determine the next steps for the mission. So that's the story so far. Now let's move on to the future and look at the next slide and look at our strategy going forward. The mission that we've set for ourselves is complex in its own right. We want people to join the community that we are building. What we want is for people to gather together and share knowledge, and we can build that knowledge among our community as we all learn more about how to handle complexity in our different environments. The strategy has 4 different elements, and I just want to talk a little bit about each of those on the next slide. The first of these is to convene, as I've said, and to build a community. We've already made a start on building that expert community around the mission, and it's played a key role in getting us this far. But we want to continue to build and diversify this community globally, because we know that different cultures internationally approach safety and risk management in very different ways, and we believe that we can all learn from one another. We also need to better connect to the thinking of academics and with the safety professionals in industry, so that we can create safer practices and policies that practically address issues that make complex infrastructure systems safe or unsafe. And we will need to work, as I've said, in an interdisciplinary way if we are going to maximize that sharing of knowledge between engineers and non-engineers, and to make all sectors as safe as we can. The second element I want to talk about is that of governing. Governance of complex structures and complex systems creates the environment in which it is built and in which it operates. It can be a catalyst for contributing towards, rather than helping to prevent, systemic failure. As systems evolve to increase complexity, there's a need to develop a legal or regulatory system that recognizes that complexity and responds appropriately. And again, Roger will expand on some of this in his presentation later. Later in the year, we are hoping to hold a governance of complex systems roundtable to scope this work stream further. And if you would like to be involved after you've heard this briefing today, please do contact Shelley, our program manager. Now I want to talk about advocating. When catastrophic systemic failures occur, there is nearly always someone who has predicted it and raised concerns, and yet no one has taken preventative action. Those people who raised the concerns haven't been listened to. One of our goals is to prevent this from happening by proactively changing culture, mindsets, and behavior within communities that develop, operate, and use complex systems so that we can help engineers mitigate against long-term threats to safety and to listen to those voices around them. Similarly, we're in the process of developing this. We're talking about work in progress here and scoping this important initiative, and a roundtable will follow soon. So again, do let us know if you want to get involved. And finally, I want to talk about where this fits within education. As the world becomes increasingly complex and unpredictable, we must ensure that we secure adequate levels of safety. We believe that means we need a radical rethink of what is and is not in an engineer's education, and we need to better understand how we train our engineers so that they have the necessary competencies to understand and manage issues arising out of complexity and to lead in delivering safety. In addition to this, as things get more difficult to predict, and we can no longer base our understanding or our approach to safety management on things that have already happened and which we can learn from, we know that we need to develop new tools because our existing tools may not be suited to the new context that we find ourselves working in. We believe we need to develop new safety management tools, as well as continuing to use the old tools, but recognizing their limitations when dealing with new problems. As part of this Educate workstream, Safer Complex Systems has commissioned 19 case studies to date, 2 of which Roger and Danielle will be talking about in a moment, which will examine complex system successes and failures. The case study work will be assembled as part of that learning resource and will show us what we can learn from things that have worked well or which have gone wrong in the past, and it anticipates what we may need to do to stay safe in the future so that we can all learn to live in a complex society in a safe way. To create impact, we will be using the case study learnings to support the education and professional development of engineers in academia and industry, also sharing it with policymakers, senior business leaders, and other stakeholders. We expect that this case study work will form the basis of our support for practitioners who are tackling similar challenges arising out of complexity, but working in very different contexts, whether that's sectors, geographies, disciplines, but also help them to better connect and learn from one another. And so finally, from me, before we move on to Roger, on the next slide, finally, I just want to note that here is a snapshot that shows the breadth of the contexts of those current 19 case studies and what the awardees are working on. We hope that this slide helps to highlight the importance of interdisciplinarity and cross-sectoral working to achieve this mission. Case studies pictured here examine things that range from the vulnerability of rural communities threatened by wildfire in North America, resilience of humanitarian supply chain crashes affected by the pandemic, systemic vulnerabilities in nursing home care in Australia, rail accidents in the UK, dam failure and flooding in Australia, structural integrity in offshore energy infrastructure, and many more. So now I would like to introduce both Professor Roger Kemp and Danielle Antonellis, two of our case study awardees, who are going to deliver the remainder of this technical briefing before I chair the Q&A session at the end. Thank you, and I hope you enjoy the rest of the briefing.
Good morning. I'm Roger Kemp, and on the next slide, I'd like to start with a couple of definitions. There are some phrases that we always use, but nobody really says, what do these mean? The first one is, what's a system? And as it suggests on the slide, it's any collection of people, machines, and processes which cooperate to accomplish a common goal. So, for example, test, trace, and isolate systems for COVID-19 count as a system. And the goal only emerges when the components operate together. It's not a property of any one of them. So just having the labs, just having test kits, just having call centers doesn't have any effect. The next definition on the next slide is when we use the terms engineered systems versus ad hoc systems. And you'll find this a lot in the correspondence we've been talking about earlier. So engineer doesn't necessarily mean traditional engineering. You could argue that a string quartet playing Beethoven is actually an engineered system. There's a very detailed specification, the music, they know how long it's going to take, they know exactly who's involved in it. It's well defined. On the other hand, an improvised jazz session could be something totally different, where there is no fixed number of people, it's not obvious how long it's going to go on for, and it's not even obvious which instruments, if any, are going to join and play. So this is a definition really between engineered systems and ad hoc systems, and they have very different risk profiles. The next slide shows a failure of an ad hoc complex system. This is the 2008 financial crash. Nobody knows how many people were involved in the financial system at that time. There were probably some 50,000 stockbrokers around in Europe, some 100 or 10 million rather individuals in US trade shares individually, 25,000 banks, all doing their own thing, all working in their own corner, all aiming to optimize their own part of the system. No overall central regulation and no real understanding of how this lot goes together. This was very definitely an ad hoc system because it just wasn't defined. The next slide talks about how we're going to develop an engineered system. And here on the left-hand side, you can see all the various trade-offs that are necessary to define the objectives. What's feasible? What do we want to do? How do we best trade that off? There's a systems authority, systems architecture, eventually that produces a series of specifications at the bottom. These then go into the manufacturing side, development, build, test, all the individual bits work together, they're integrated, and finally, you get an operational system. This works well with an engineered system and can be a very effective way of managing complexity if you know what everything is involved in doing. It becomes more interesting if you then expand this where you have lots of different systems all coordinating with each other. So the next slide basically takes what was on the previous slide and multiplies it by 5. And here you've got 5 separate systems all interacting by fairly indeterminate ways and all eventually producing some sort of input to society as a whole. And this is where life becomes really challenging, because you've in effect got a complex system of systems, and quite often you don't know what the interactions are between the various systems. This is shown on the next slide, which is a collection of linked systems that we discovered in Lancaster when there was a complete loss of electricity as a result of Storm Desmond in December 2015. We lost electricity. That also impacted all these other systems. There are some that you expect to lose. When you lose electricity, the lights go off, okay. You perhaps don't think, though, that you can't fill up your car with petrol because the petrol station has electrically operated pumps. You probably don't think that all your mobile phones will go off because, after all, it doesn't use your local electricity. You probably don't think also that the railway might shut down, not because it can't run, but because none of the facilities in the station to allow it to run are existing. So this was a situation where you had basically an ad hoc collection of subsystems that came together, and nobody really was expecting quite the interactions they had. And now I'd like to jump back to an engineered system. And on the next slide, I'm looking at who is actually responsible for an engineered system. It could be the owner or the main contractor. Before privatization, Central Electricity Generating Board in Britain, in France, SNCF, the French railway operator, quite clearly the person responsible for a system. It could be an international standardization committee. Mobile phones, for example, have very complex standards to make sure you can use them worldwide with any number of different infrastructures, or the World Wide Web, which again has a very comprehensive arrangement of standardized system standards. It could be a consortium set up to cover a particular system, or it could be a dominant supplier. It could end up, in fact, being the government. For example, in the UK, the test and trace system is almost certainly a government activity. The next slide shows a picture that is a case study mentioned in the York report. And this is a failure of an engineered system. It was a Uber self-driving car. Car, as you can see on the right, taken from the New York Times, struck a pedestrian who was pushing her bicycle across the street. In the next slide, I've taken a page from the official accident investigation report, which just shows a number of different sensor systems, cameras all around, a top-mounted LiDAR unit, radar, proximity sensors, absolutely everything. It was really detecting what it could see, or what there was around it. The problem is shown on the next slide, which is the time history. And although it could see all this, it frankly didn't know what to make of it. So on the left-hand column, time relative to impact. On the third column from the left, classification, what it could see. And if you go through the official report, it said, it's a pedestrian. No, it's not. It's a bicycle. No, it's not. It's something fixed. Oh, it's a pedestrian again. It's a bicycle. It was only 0.2 seconds before the impact that it worked out it was a bicycle and that it was actually heading into the lane of the SUV. How would people actually do this job rather than the computer? And the next slide shows how individuals would work out how they were working in this situation. Firstly, they'd perceive their environment, they'd use all their senses, they'd look at the cues, to try and decide on the relevance. Then they'd try and understand the current situation, integrate all that data, create some meaning from that. Then they'd extrapolate to the future, estimate the dynamics of what's doing what, produce a good mental model, probably do a risk assessment, and then predict future state. So driving a car is actually to be a component of a complex system of systems. And human drivers are usually pretty good at anticipating the actions of another human, even if they're doing something they couldn't have imagined. Big question actually is, can the computer do the same? I think the Uber example shows that certainly 2 or 3 years ago, that they weren't very good at this. It won't be many years, perhaps, before this definitely changes. In the next slide, I look at what actually indicates complexity. And here just a number of items that come up time and time again in the various case studies we've been looking at. Firstly, large numbers of participants all sharing responsibilities. A wide geographical or organizational distribution of a single critical system, all sorts of interdependencies between various systems. Many actors, all with their own incentives to optimize their own corner, and the system continually adapting to fit into its environment. As Dame Judith has mentioned, we asked the University of York to suggest a framework for describing complexity, and that's shown in the next slide. Here you can see on the left the causes of system complexity, much like the previous list I've just put up. Then central, some of the consequences of system complexity, and to the right, the systemic failures that might arise from complexity. And coming down from the top, you can see all the possible exacerbating factors that make things generally worse. But we have a number of controls. We have design time controls where we try to design in a safe system, and operational control, operation time controls, where again, when the system's operating, we hope them to be managing it safely. York identified basically 3 levels of responsibility within this structure. And the next slide shows those layers of responsibility. At the top, governance. This is something Dame Judith's already spoken about: national jurisdictions, regulatory bodies, laws, regulations, standards, and so on. Management, decisions taken by the management team involved, and what York described as the task and technical layer, working into the complexity of the system itself, the environment, and all the human system interactions. Next slide discusses some of the potential failures of governance. And here are just a few of them: unrealistic timescales, badly defined objectives, dysfunctional management, responsibility split. And one that I'd like to talk about in more detail, which is the political restructuring of a system and political responsibility for possible failures. The next slide shows a picture of the train crash at Hatfield in the UK in October 2000. The rail had fractured due to rolling contact fatigue. Train derailed, there were 4 fatalities, 70 people were injured. There was a formal inquiry, as one would expect, and it basically blamed the contractor for poor maintenance and the infrastructure controller for not managing them better. The infrastructure controller, Railtrack, suffered a loss of confidence. It was declared bankrupt, and in effect, the infrastructure was nationalised and taken over by Network Rail, which manages it to today. But was it quite as clear-cut as that? On the next slide, which comes from a government report, you can see the financial subsidy to the rail network. And during the time it was managed by British Railways, back in the sort of 1980s, early 1980s, subsidies were running around about 2 to 3 billion pounds per annum. The privatisation activity, which split the network into more than 100 different companies, a lot of them negotiating with each other, having contractual terms and conditions with each other, all with shareholders who want to be satisfied, was a bonanza for lawyers, but added a lot to the overall management and administration of the railway. But in fact, the total subsidy didn't increase. After Railtrack's demise and Network Rails took over, you can see that the subsidy increased from about 2 billion up to sort of 6 or 7 billion. So I think one has to really ask the question, was the accident really entirely the fault of the maintenance contractor and the administration of that contract? Or was it at least in part the responsibility of a government which by changing the overall structure had left the railway without enough money to actually carry out essential maintenance. There's another example of a case study on the next slide, which talks about Brisbane floods. Now, there were some fairly serious floods, and you can see that there were three reservoirs basically upstream of Brisbane. These have two totally different functions. One, they're to manage the wet season flooding, and two, they're to provide water storage so you don't get droughts in the dry season. And these are absolutely conflicting objectives. On the one hand, if you're trying to manage a wet season flood, you want to start with empty dams so that however much water falls, you've still got somewhere to put it. Looking at the dry season problem, you really want these things to be absolutely full at the end of the wet season. So how on earth do you manage this? This is a genuinely complex system. And going back to the York model, there were a number of exacerbating factors. Unpredictable climate due to climate change, a lot of houses built on floodplains, meaning that the city was actually far more susceptible to floods than it might otherwise have been. More homes meant more demand, so greater demand for water, and all sorts of conflicting political objectives. So there are a few of the studies we've looked at, both in the York report and also in the case study arrangements that we were talking about earlier. And now I'd like to pass over to Danielle, who'll be talking about a very specific case study that she'll tell you about.
Thank you, Roger. Next slide, please. Thank you. And I also want to thank Engineering X for the opportunity to speak today and for welcoming the Kindling research team into the Safer Complex Systems program through the case study initiative. A quick introduction. So my name is Danielle Antonellis. I'm the founder and executive director of Kindling, which is a US-based nonprofit founded in 2020 to connect fire safety knowledge to local and global humanitarian development efforts to reduce the unequal impacts of fire on people, property, and livelihoods in vulnerable communities around the world. And today, I'm not only presenting on behalf of Kindling, but also our wider research team from Stellenbosch University and the National Fire Protection Association, as well as John Twig and Laura Hurst, who are working as independent consultants on this project. And today, I'm going to be speaking about ad hoc complex systems using our case study, which is a comparative study of fire risk emergence and informal settlements in Dhaka, Bangladesh, and Cape Town, South Africa. Next slide, please. But before jumping into the case study, I want to share this cartoon. You can see 6 blindfolded people were positioned as shown and asked to describe what they felt. That's easy, said the man holding the elephant's trunk. It's a snake. The one holding the elephant's tusk said, it's not a snake, it's a spear. And the man sitting on top of the elephant played with his ear and said, no, this is a fan. And as you can see, it goes on with people feeling different parts of the elephant. But not one of these people actually saw an elephant. And with complex systems, and especially ad hoc complex systems, there is never a single owner and seldom a single person or organization that can have a full view of the problem when looking from only their perspective. People perceive risk differently, and so engagement with diverse stakeholders is critical to develop an understanding of the system, potential safety issues, and to identify and develop potential solutions, or better yet, system upgrades. Next slide, please. So leaving the elephant cartoon behind, I also want to talk about the dynamic and constantly changing nature of our world and therefore of ad hoc systems. Our case study sits within the context of urban development, and cities are not static, they're alive, they're dynamic. While there are top-down systems of governance and control that shape or at least influence how cities develop, much of how we interact with each other in the urban environment is ad hoc. It is driven by personal decisions, and our daily experiences are characterized by systems we interact with, both engineered and ad hoc systems. Collectively as society and cities, we are really talking about systems of systems. Next slide, please. While urbanization can offer opportunities for sustainable growth, the speed and scale of urbanization bring considerable challenges. Demand for urban housing, demand for well-connected transport systems and other infrastructure, basic services, jobs, And when you layer on the challenges with poverty, social and political marginalization, systemic and historic discrimination, displacement, inequalities, etc., we see that actually informal settlements or unregulated human settlements are growing in number and size. And today, over 1 billion people live in informal settlements, including 30% of urban dwellers globally. Informal settlements are not planned or regulated by the government. People occupy public or private land, often with insecure tenure, and build or rent homes, generally with poor construction. These dwellings might be a single floor, or they might be up to 4 or 5 or even 6+4s, as you can see on the right-hand picture from Mumbai, India. As you can imagine, informal settlements are incredibly heterogeneous and diverse in terms of the built environment and, of course, with the communities that occupy them. And informal settlements are really physical manifestations of people's resourcefulness. They are ad hoc systems developed by individuals and communities to help them meet their basic needs: housing, energy, transport, water, and more. Informal settlements are the outcome of shortages of public resources and the consequent incapacity of the state to provide basic services such as water, electricity, or waste collection. Informal housing is a response to these problems rather than a problem by itself. Next slide, please. But informal settlements are far from a perfect solution, and the state should be regarded as complicit in the scale of informal settlements and associated practices. Informal settlements are often characterized by people living in slum conditions, where residents have no security of tenure, don't have access to basic services, and are cut off from the rest of the city. Social issues often affect these areas, and informal settlements can be quite hazard prone, especially to fire. Next slide, please. Fires are frequent, and they spread with devastating speed due to physical factors such as high density of buildings and the use of combustible construction materials such as plastic tarpaulins, bamboo, timber, and even cardboard. Fires cause deaths, injuries, loss of property and livelihoods, displacement, and more. But despite fire's disastrous impacts, fire risk reduction is seldom integrated into disaster management policies and practice, nor into development planning. Over the past 5 to 6 years, there's been an emerging field of research into fires in informal settlements. Much of this work has been led by fire scientists and engineers aiming to understand fire risk factors in informal settlements and the unique fire behaviors observed in these settlements. There is growing recognition, though, that these fires are not just technical challenges. These fires are social and political problems. And there's a need to step back from detailed engineering analysis and to apply systems thinking to this problem. Next slide, please. And so this project that we're doing really revolves around this one sentence. Fire risk itself emerges from complex urban systems, their interactions and interdependencies. Next slide, please. This slide shows just some of the systems that lead to the emergence of fire risk. Fire risk is an emergent property of these interactions between engineered and ad hoc systems: housing, economic activities, energy, supply chains, waste, etc. The slide also shows some of the systems that support fire response and fire safety more generally: water, roads, communications, healthcare. And while fire risk is a property of complex systems and their interactions, fire safety can actually be considered a system in and of itself. Next slide, please. Now, when we talk about urban fire management, we're typically talking about top-down management from a regulatory perspective, thinking about fire services, urban planning, etc. But as we've just discussed, fire risk itself is emergent, especially in informal settlements where top-down regulatory systems are not relevant and decisions are often made at a personal or community level. A critical question then is, who is responsible for fire safety in informal settlements? It seems easy to blame governments, and while they do have a critical role to play, so do other stakeholders. We don't currently understand the wider governance context related to fire safety in informal settlements that shapes how decisions are made and how issues are addressed. Our project aims to better understand the emergent nature of fire risk and the causes and impacts of fire and management of fire risk. We're focusing on Dhaka and Cape Town because these cities face challenging fire issues, but they're actually quite different: physically, politically, socially, economically, and more. And ensuring safety of systems is not easy. Holistic systems of fire safety need to be developed and sustained, including investments in fire response infrastructure. But we also need to ask ourselves, how can we promote the emergence of fire safety from the bottom up or from the middle outwards? Fire safety itself actually often emerges too, through learning from people's lived experiences and knowledge sharing through generations and communities. There are likely many fires in informal settlements that are never reported because people respond quickly and limit fire spread. A few years ago, I was in Cape Town engaging with creche owners in informal settlements about fire safety. One woman told me that fires start because people come home from the spaza or pub late at night and cook food, but then they fall asleep and knock over the stove, causing a fire. She said when she smells her neighbor cooking food late at night, she gets worried about fire and knocks on her neighbor's door to make sure they're awake. This is just one example of a positive emergent fire safety practice. Next slide, please. To explore and describe how fire risk and fire safety emerge in informal settlements, we're using an adapted pressure and release framework, which is a classic disaster risk reduction crunch model that has been applied to a wide range of contexts and is generally considered to be an accessible framework, not only to researchers, but also to practitioners and engagement with key stakeholders and the public. This framework emphasizes that both hazards and vulnerabilities need to combine to have a disaster. And it demonstrates that vulnerabilities are rooted in socioeconomic and political processes. The original framework is intended for natural hazards only, but we've adapted it here for urban fire. The critical difference is that not only vulnerabilities are rooted in socioeconomic and political processes, but also the emergence of fire hazards. This framework also aims to communicate that people can intervene in a complex system by spotting connectivity between systems not being managed properly and intervening tactically or strategically. This can be done by individuals or entire communities, as well as by external stakeholders. For example, fire safety can be promoted through emergency planning, community capacity building initiatives, and more. Reset Faisal, which is Kindling's research director, for example, developed a community-based fire safety program in Corral Informal Settlement, Dhaka, while he was working at BRAC, which included fire safety education from the fire services, fire drills, waste collection initiatives, networked fire detectors, and more. To explore how emergence of fire safety systems can be promoted, we are asking ourselves a lot of other critical questions, such as what is the enabling environment or disabling environment for improving policy and practice? Who are the key stakeholders? Who is harmed by fire, and does anyone benefit from it? What are the formal or informal and roles and responsibilities and mandates of different stakeholders? And what are their visions and perspectives of the fire problem and how to address it? Much of this relates to the general principle of the political economy of urban fire management. Next slide, please. Finally, our approach aims to explore how those political and social dimensions can be integrated into complex systems analysis. We also hope our project will help to bridge complex systems theory and practice with the disaster risk reduction in urban resilient spaces. You can see here some of the different threads of our methodology, which we're exploring. But that's all for me today. So thank you so much for your time and attention. And back to you, Roger. Thanks.
Thank you, Danielle. The next slide summarizes what we've been talking about for the last half hour or so. I think the most important point is that modern life involves many complex systems. Mostly they're unplanned, ad hoc systems, and they're getting more. The growth of IT has actually enabled far greater complexity. A few years ago, you would never have considered buying, I don't know, broccoli from Kenya or somewhere, just because of the complexity of the financial transactions. Now with computers, it's easy. Often complexity and all the invalidated assumptions are not actually recognized. Stewardship of governance of complex systems is unlike anything we've seen before. It is not the simple manager responsibility incident sort of activity that we have traditionally thought of in terms of the way that we manage safety. And finally, education and training need something of a revamp to actually cover all the complexity of how we're going to manage complex systems in the future. So thank you. I hope that there's still plenty of time for some questions.
Thank you, Roger and Danielle. So, thank you, thanks everyone for your presentations so far. I just want to kick off this session by just maybe adding a few observations of my own. We've tried to give you a sense in this short space of time about the breadth of what we're trying to cover here. I know that many of you on this call will already be working with complex systems within your own discipline, but in some respects, we're lifting this debate up to a level of that's really about that interdisciplinarity and extending this beyond engineered systems. So let's move on to look at some of the questions. So Lawrence Chapman has asked about whether digital competencies within our engineering community need to be improved to enable safer complex systems. Roger, I'm going to ask you to come in on that one. Do you see digital competence and capability as being an enabler or an additional complicating factor?
I think it depends so much on what sort of complex systems you're thinking about. If you're looking at basically an ad hoc system of the sort Danielle was talking about, then trying to make a digital twin of an informal community in, I don't know, South Africa or India or wherever is always going to be a bit of a long shot. I think for some engineered systems, a digital twin is actually very useful, but perhaps one of the benefits is actually that in trying to write the specification for the digital bit, you're actually understanding better what the real system is and how it works. So I see that as being probably one of the stronger outputs, rather than saying, great, we now have a digital twin for how this, I don't know, complex life support system in a community works.
Okay, thank you. Question for you, Danielle, from one of the people listening is what benefit have you gained from being part of the interdisciplinary cohort of case studies? Has it been helpful to you in your work to liaise with others from other disciplines?
Thank you. It very much has been. I suppose there's almost 2 layers of interdisciplinary working on our project. There's the first layer within our team itself, and we have 9 people on the team from different contexts and different backgrounds, which has been really fascinating. But then, yes, as being one of the 19 case study awardees has also been a really valuable experience. If you look at the list of the different case studies, they're incredibly different from each other, at least at first glance. But there's actually a lot more common challenges between them. And we have sessions with all 19 case study awardees or leaders, and those are really fascinating discussions. We also have kind of catch-ups every week and peer-to-peer reviews and things. So there's all sorts of opportunities to kind of engage with other case studies. And I wasn't surprised, for example, that our case study on fire, related pretty closely to the wildfire case study in North America. But projects like the Social Innovators as Human Sensing Network, that really surprised me that there's actually quite a lot of parallels between our work and that project that Matthias is leading. And it's really because that's an ad hoc system as well. So there's just, I think, yeah, exactly like you said, Judith, like looking at it from, almost above the discipline boundaries that we normally think about or that we're normally constrained by, and really just understanding complexity and the different types of complexity and properties, and being able to kind of engage with people that think about things quite differently has been really valuable to get us to think about our own project in a different way.
Okay, thanks. And following on from that, another question that someone has posed is, shouldn't we be working on more industry-specific examples? For example, oil and gas or chemicals. The question is really whether or not practitioners will struggle to apply learning from things that are so abstract rather than specific to their discipline. What's your view on that, Roger?
I think it's relatively easy to think of a complex system within a controlled and managed industry. It's far more challenging to think of an ad hoc system that includes all sorts of things that particularly unpredictable human reactions, particularly wide geographical spread. Yes, I agree we should be looking at industry, but I think that's the easy one. I think it's really important to have a few of these horribly complex international, flexible, ill-defined systems in order to say, well, how far can we actually extend our knowledge? Because if we can concentrate our efforts on relatively straightforward, relatively simple things that exist and that we think we can manage, we're probably kidding ourselves that we've actually got complex systems under control.
Okay. Here's an interesting question. I'll leave you to decide which one of you volunteers to answer this one. How easy, or indeed difficult, is it to define even roughly the boundaries of a system of systems? I like that question.
I'm happy to jump in first, and then maybe Roger, if you want to jump in. I think it's difficult.
Me too.
Yeah, I think, for some systems it's more obvious than others, but I think you kind of have to choose how you're going to define it. I don't think there's like a right answer necessarily. It depends on what you're trying to understand about the system sometimes as well. So for example, with our research into fire and informal settlements, we've been debating this exact question on the team and we haven't come up with an exact answer yet, but I think geographic boundaries is where we're leaning, because we're talking about systems to systems, like within a particular area where people are affected by potential fire issues. Previously to Kindling, I worked at ARUP, and there was a really interesting project on water resilience in cities. And they traditionally people use geographic boundaries around the city, or the jurisdictional boundaries. And ARUP realized that actually the watershed was a more appropriate system boundary, which went outside of the city into mountainous areas or into other areas. So it really depends on what you're trying to understand, I think, in my experience. But yeah, not easy at all.
Roger, anything to add to that?
Basically, I agree that it is very difficult, and that going back to that example I gave about the floods after Storm Desmond, there were a whole load of subsystems and other systems that people never really thought were part of the same overall connected network. And it's only really when you've had a failure and you think, oh my God, we should have thought about that one, that you actually are able to answer the question. So I'm sorry I can't be more specific.
Not at all. Okay, I'm going to volunteer to answer this next question. The question is, was it difficult in obtaining support from all stakeholders for this program, or did they get involved from the start? Have we received support from multidisciplines? The answer to that question is easy. So I answer the easy questions. I get the others to do the difficult ones. We've had enormous support from the outset for this program. One of our early challenges, and Roger will remember the days when we agonized over whether or not we needed to define what we meant by complex systems. But what was really interesting was that the very first workshop that we had, when we laid out the proposition to people that said, and this was pre-pandemic, we think things are getting really complex, and we think the complexity is getting more and more, and our tools to deal with that are not good enough. We didn't need that definition. People got the problem. People shared that concern, and we've had multidisciplinary and non-engineering support for this program from the outset. And I think that's one of the things that's really exciting about it, is that we're building our knowledge as we go. We're all on a journey of discovery, and there's a lot of enthusiasm and a lot of people who see the need for this work. The next question is for you, Roger, and it says, I was interested in your financial markets example being described as an ad hoc system. Some financial markets often have high entry barriers, for example, specialized knowledge, and are often criticized as being too engineered. Should we always incentivize ad hoc markets to become more engineered and thereby open them to criticism on grounds of for example, diversity or being high entry barriers, is being ad hoc, just something we have to put up with, recognise as part of our quest for wider access.
I think this brings into question quite a lot of political aspects and political choices.
Yeah.
Remembering back to the 1960s, 70s, it would be quite normal to say, we have a financial market, it is well controlled, we know exactly who's in it, we know exactly how it works, and we have a regulator that knows the first names of everybody involved in the process. That was relatively straightforward, but politically, that isn't really an option anymore. The whole sort of Western, particularly Anglo-American view of life is that the market, private enterprise is king, and therefore we have to work with that and with an open system. And I think that politically to say we're going to in future to restrict financial markets only to registered people who have filled in the appropriate risk assessments and everything else would be a bit difficult. But frankly, I'm out of my depth here. This is somewhere where I suggest we basically need someone like the chairman of the Bank of England who's prepared to talk about that. But it does feel to me that trying to go back to everything being engineered and regulated is going to be impossible.
Yeah, absolutely. Absolutely. Okay, there's another question being asked about whether or not we've looked at the use of bow tie diagrams, and many people on this call will know what is meant by that. Bow ties are one of the existing tools which are used in some disciplines for looking at complex systems and interactions between different systems. Well, yes, we have looked at that. Yes, we do know about the existence of those tools. Clearly, and I guess part of our goal as part of this program is both to make those tools more widely available from disciplines where they are very commonly used and very well known into other disciplines where they may be appropriate, but also, as I said in my opening remarks, to recognize that in some of these complex systems that we are looking at, that may not be a suitable tool, and there may be other tools that we can be used. What we want is to build up that bank of tools and techniques that we can all use and share them across all disciplines. A question now about the education part of this remit. We've mentioned that education needs to change in order to address these issues in future. What would the panel say needs to change and needs to be added into engineering programs to meet that goal?
Shall I kick off as an engineer, and we're talking about engineering programs at the moment? I think if you look at an awful lot of university undergraduate courses, and for a while I was an accreditor for professional engineering institutions, so quite a few universities, it all really is fundamentally about bits of detailed technology. Very few courses start by saying, what is a system? How do we actually work this structure? How do we make a system stable? And then we start thinking about the technologies that go into it. So I think there's going to be a very different view of life, that a lot of the detailed calculations that one traditionally does in engineering courses, do you need to do them when you've got software programs that will do them more quickly? Obviously, you need to have a fundamental concept as to what you want the program to do, but I think one could leave out an awful lot of the mathematics, giving space for people to look at significant issues like, how do you deal with human-machine interaction? How do you design for human-machine interaction? To teach a course to students where they spend their life looking at finite element analysis and structural materials and whatnot, and then to put them into a job where the first thing they probably end up doing is to work out how the controls for a particular piece of equipment actually have to work with real people at real places. I think it's an unfair way of going about things, that we need to change and think through, what do engineers in the future actually have to do?
Great. Shelley, sorry, Danielle, would you like to add to that? Sorry,
Yeah,
Shelley.
I'll be very brief. I'll be brief because I know we're coming to the end of time, but I think just in addition to thinking about systems thinking in school, we also need to think about closing the gap between physical sciences and social and political sciences. I certainly didn't have any social or political science courses when I was in school, in engineering school. And now I've learned a lot of it on my own, and I wish I would have had it earlier. So I think there's certainly opportunities to just bring disciplines closer together at an earlier stage. I think in education is a great opportunity for that.
I think that's a great answer on which to close this technical briefing session. So I would like to bring this all to a close by thanking everyone for participating this morning. I hope that we have whetted your appetite for getting involved in this. As I said, we already have quite a strong community built. Danielle has shared with you her own personal experience of how valuable it's been to be part of this multidisciplinary community. So I just really want to emphasize that every one of you who has joined us today is more than welcome to join us, both to learn and to share your knowledge. And we look forward to working with you as we take this, what I consider to be really exciting and groundbreaking work forward. So Shelley has sent you a message with a link to the strategy and her contact details if you do want to join that community and be part of this. I'm sorry to those who posed questions that we've been unable to answer, but we will try and produce some further material to respond to some of those and share it with that community. But in the meantime, I just want to say thank you to everyone for joining and for listening and participating. Some great questions. And I hope we'll see you again at future briefings. The next briefing in this series will be on healthcare systems in September. That's not a safer complex systems briefing, but it is a Royal Academy of Engineering briefing on health systems and healthcare. But thanks everyone, and look forward to continuing to interact with you as this work goes forward. Thanks a lot. Bye.